This generated image of a PagerDuty alert points to a precise moment of failure. At 2:47 a.m., an automated pipeline at Cascade Freight died while parsing a nightly batch of EDI load tenders. This dense 200-line procedural monolith tangles every operation inside a single main loop. Deep in that structure, at line 137, we find a naked accept exception pass block. The original author encountered a parsing error and instructed the program to swallow it silently. Suppressing the exception at that depth creates an immediate mechanical consequence. The script fails to process the shipment data, but because the error is caught and ignored, the process does not terminate. The file pointer remains open, and the pipeline hangs silently in the background. That silent hang accumulates quantifiable financial damage. Without a functional pipeline, 4 hours of incoming EDI 204 load tenders pile up unprocessed. Loads sit pending in the yard, resulting in roughly $6,720 in detention penalties and late fees for a single unhandled error. The post-mortem for this event isolated the exact engineering flaw. The script raised an error at the leaf of the program, a deeply nested helper function, and swallowed it there. The top-level functions remained completely blind to the failure. Indiscriminately wrapping lower-level functions in try-except blocks does not make a system resilient. It guarantees that when failures inevitably occur, they happen silently and catastrophically, stripping the system of its ability to recover or alert an operator. A frequent misconception in software design is treating all runtime errors as identical events. If the program throws an error, the instinct is to write a catch block to prevent a crash. This split-screen diagram maps Dave Pacheco's framework, strictly dividing software failures into 2 distinct categories, each requiring a different handling strategy. First are operational errors. These include missing files, malformed strings in a data payload, or severed database connections. These are expected environmental conditions. The code itself is written correctly, but the outside world has failed to uphold its end of the contract. The program must negotiate these conditions as a normal part of its operating envelope. The strict handling rule here is that operational errors must be returned to the caller. They are structured data points indicating a specific failure, and they must be passed up the chain so the program can decide how to route the problem. The second category contains programmer errors. These are bugs, passing a list where a dictionary is expected, attempting to read an attribute from a none type, or writing an off-by-1 error in a slice. These represent fundamental logical flaws. A program cannot intelligently negotiate its way out of broken syntax or a broken memory reference. Therefore, the handling rule for programmer errors is strict non-intervention. The code must crash loudly and unhandled. This forces the system supervisor to restart the process and immediately pages the on-call engineering team to fix the code. Catching a programmer error actively hides a bug, allowing corrupted logic to continue executing. Failing to return an operational error cleanly drops external data. Knowing what type of error you are dealing with dictates exactly where in the architecture it must be handled. We must translate this error taxonomy into a physical layout within the codebase, separating the functions that do the work from the functions that handle the failures. This diagram maps the code execution flow into 4 distinct concentric layers. In the center is the leaf layer, small, pure helper functions containing absolutely 0 try-except blocks. Surrounding it is the domain band, containing pure functions responsible for parsing text, validating rules, and shaping data. When the domain band encounters bad input, like a malformed shipment record, it raises a typed domain exception. It never attempts to catch that exception. Moving outward is the transport band, managing I/O and network APIs. If a connection drops, it raises an operational exception upward. Finally, the outermost ring, the boundary. It follows a non-negotiable rule. It contains the program's single try-except block. Look at how an operational error travels through this structure. A malformed line raises an error in the domain band. The error passes cleanly through the transport band and bubbles all the way up until it is caught at the boundary. If an engineer violates this structure and catches the error at the leaf, the boundary becomes deaf. The main execution loop has no idea a failure occurred, and therefore has no context to dictate how the pipeline should respond. Forcing all operational errors up to a single boundary is the only architectural way a program can safely coordinate complex policies. Only the boundary has the broad context required to halt an entire batch of files, or simply log a single bad line and continue processing the rest. Architecture diagrams are conceptual. To enforce this concentric boundary in a production environment, we apply strict, modern Python standards to the codebase. This diagram illustrates the code transformation. The procedural monolith is dismantled into isolated modular functions, mapping cleanly to our 4 architectural layers. To guarantee exact input and output shapes, we apply PEP 484 type-ins. Every argument and return value must declare its exact structure. Next, PEP 257 docstrings require public functions to declare failure modes in a raises clause. At the boundary layer, the catch block must be explicit. We replace generic catch-alls with specific exception families, catching only Cascade EDI error and OS error. Everything else, including programmer bugs, bypasses the boundary and crashes. Catching the operational error is only the first half of the boundary's job. Once caught, the failure must be documented through structured observability. This comparison highlights the flaw in traditional F-string logging. Shoving variables into a sentence creates an opaque string blob that an ingestion pipeline cannot query. Modern observability standards solve this by pushing context out of the message and into a dedicated searchable attributes dictionary. That dictionary requires a strict shape. It must log the event type, the specific record ID that failed, the internal engagement ID, and the exact error class. When the logging platform receives this payload, it extracts those specific dictionary keys and elevates them into searchable top-level database columns. An engineer investigating a failure can now query the logs directly by the shipment record ID. This observability relies on absolute consistency. If an engagement ID uses a loose, client-provided string instead of a canonical internal format, schema drift occurs and the database queries break. Strict type hints, explicit docstrings, and searchable structured logs eliminate ambiguity. They transform a fragile, unpredictable script into a rigid, observable contract with the operating environment. This multi-pane dashboard tracks the outputs of a successful refactor. The 200-line script is now a strictly typed module, broken down into discrete functions, validating cleanly against a strict linter. To verify the boundaries hold under pressure, the module is tested against 4 distinct fixture scenarios. The test suite asserts that the code handles perfect inputs, raises exceptions for malformed lines, survives missing files, and securely manages partial batch failures. The entire structure relies on a single mandate. Operational errors must route cleanly to the boundary as structured data, and programmer errors must bypass the boundary to crash the system. A Python pipeline is only production-ready when its failure modes are engineered, typed, and tested with the same rigor as its success paths.